reversible, partly reversible square, as same as on the previous page. But now I do take another network, my auxiliary network, which is the same, just two diagonal reactions are added. And I take the original rate constants I denote by kappa. The new on the new network, my auxiliary network has rate constants denoted by lambda. Then, and this is the key and main idea, once I fix my kappas, can I find lambdas such that the two differential equations are equal, identical, and maybe the second one is vertex balanced? If that's the case, then I can conclude for the original network that a classical Horn-Jackson function is a global Lyapunov function. So what does it mean? I need to check two conditions. The first condition is DE stands for dynamically equal. This just refers to the fact that the two differential equations are identical. I need to match one by one kappa 1 must be equal to lambda 1 plus lambda 7, and so on. And additionally, as I said, on the second network, my goal is to have vertex balanced, uh, vertex balanced rate constants. And vertex balancing on the second graph is like this. So what I ask is that for a fixed kappa, does there exist lambda rate constants and an equilibrium xy such that all of these hold? If this is the case, then I'm gonna say that this particular kappa belongs to not to the toric locus, but to the this guy's toric locus. And if I solve this nonlinear quantifier elimination problem, then turns out this is the solution, which is great. It's a much bigger set in parameter space than the toric locus, which I showed you on the previous page. Remember, that was a codimension 1 set. This is a codimension 0 set. It's a full dimensional set. In fact, it occupies kind of 58% of parameter space. It's an ad hoc choice, how exactly I measure that. Uh, Here I chose to take the simplex. And so if you sample from the simplex rate constants and try to figure out when is your sample in this set, this is what you find, 58%. And so we say that for this part of parameter space, the original network is disguised vertex balanced. That means we can conclude all kind of nice properties. Horn-Jackson function is a global Lyapunov function. Next example is the partly reversible parallelogram, which is again a network that falls under the scope of the deficiency one theorem. As a consequence, again, we know there is a unique positive equilibrium for all rate constants. We can talk about vertex balancing. And again, we find the analogous thing, same formula, in fact, for vertex balancing. So we know once the parameters satisfy this equation, we do have global stability. On the other hand, for other reasons, we also know that a stable positive equilibrium and the stable limit cycle can coexist for some rate constants. What can we say again about this guy's toric locus of the same network? So again, I'm gonna take an auxiliary network. Again, I'm gonna add these two diagonal reactions. For the new network, I'm gonna denote the rate constants by lambda. I play the same game as before, very similar equations as before. I have a set of equations for guaranteeing dynamically equal, that the two equations are dynamically the same, are just literally the same, and a set of equations for vertex balancing for the second one. And if I solve this, then it turns out I get the same solution as for the previous one. And so I get the same 58% of the simplex for as the disguised vertex balanced locus. Turns out this is not some coincidence or pure luck, but there's a good reason why I got the same in these two cases. It's known since 2023 that once I have a network, a Euclidean embedded graph, and I have another one, and the two are related by an invertible affine transformation, then the disguised toric locus of the original one and the disguised toric locus of the new one, the one which I get by applying the invertible affine transformation, is just absolutely the same. This is a result by Sabina, Miruna, Stefana, and Polly. And for this reason, actually, we get for free of charge that once I take the lifted parallelogram, for example, as shown here, we do know that even for that one, the disguised toric locus is just absolutely the same as for the other two. Okay, this is something good to keep in mind. This also kind of shows and explains immediately why the disguised toric locus of this network here, the partly reversible square, cannot be the whole parameter space, even though we know global stability of the unique positive equilibrium. The reason it cannot be the whole parameter space is because it has an affine transformation. There is an affine transformation which brings it to something, another network, which is not always globally stable. This is what stops the disguised toric locus from being the whole parameter space for the partly reversible square. This is something good to keep in mind. I'm going to show you a couple of additional networks. For example, a bistable network. This is an example which admits three positive equilibria for some rate constant values. Two of them are sinks, one is a saddle. For some parameter values, it admits a homoclinic orbit. For some other parameter values, a limit cycle. In fact, it admits a Bogdanov-Takens bifurcation. So it's not absolutely trivial to analyze this network. Our goal would be to understand global stability, when exactly it has a unique positive equilibrium, when is that unique positive equilibrium globally stable. It's not a trivial network or not a trivial question. What I propose is take again an auxiliary network, another network, which is the original one, just supplemented with a reversible reaction, sixth and seventh reaction. And my suggestion is the following. Once I have an original rate constant, kappa, definitely there is a positive equilibrium. It's easy to see that this network is permanent, so there will be a positive equilibrium. Call it x star and y star, the two coordinates. And with that, define my new lambdas. The lambdas on this are the rate constants of the new network, and they are defined as shown here. Then I claim two things. One is that with this choice of lambdas, the two equations are the same. So I have dynamical equality. And the second of my claims is that this second network with this choice of rate constants is vertex balanced. The only thing that needs for this to work, that I need for this to work is that, of course, I need both lambda 7 and lambda 6 to be positive or at least non-negative. And that just means my original network with kappa is disguised vertex balanced if there is a positive equilibrium x star y star, which lies in this stripe. The first coordinate must fall between these two bounds. If that's the case, then I can conclude global stability of uniqueness and global asymptotic stability of the positive equilibrium. And if I want to eliminate from this, eliminate the x star and y star from these considerations, it turns out the network is going to be disguised vertex balanced if and only if the rate constants do satisfy this condition here, which is again a full dimensional set in parameter space. In fact, if I take again my simplex, then turns out in like 35% of the simplex, a fairly large part of it, I can prove global asymptotic stability thanks to showing that the classical Horn-Jackson function is working actually. That's what happens in the background. Now, if I take another example, which I'm going to call here the Johnston-Ziegel-Sederkényi tetrahedron. This kind of network appeared in one of their papers more than 10 years ago, and that motivated us to look into it. This is a three-dimensional example with deficiency 2. That means it's going to be vertex balanced on a codimension 2 set in parameter space. Indeed, these are the two equations that the parameters have to satisfy for being vertex balanced. And my claim here is if I take this time the same network, but I redefine the rate constants, the original kappa 1, kappa 2, and so on, kappa 10, I redefine them as shown here, where x star, y star, z star is just an equilibrium, which I know exists because it's a reversible network. I don't need to know a priori whether this positive equilibrium is unique. Only thing I need is the existence. And the great thing about this is with this choice of the lambdas, the two ODEs are identical for all rate constant, all parameter values, all kappas. And the second ODE is vertex balanced, which means the Horn-Jackson function, in fact, is a global Lyapunov function for all rate constants. This was very obvious only on a very tiny set in parameter space, on a codimension 2 set in parameter space. In fact, we know it's a global Lyapunov function everywhere in parameter space, and we can conclude global asymptotic stability for all rate constants. Yet another example, the reversible Lotka-Volterra autocatalytor, which is something not absolutely trivial to analyze. So this is you take the classical Lotka-Volterra reaction, except instead of the linear autocatalytic step, x goes to 2x, you take 2x goes to 3x, and you make everything reversible. Turns out, for some rate constants, it has 5 positive equilibria, 3 sinks, and 2 saddles. Homoclinic orbit, limit cycle, all of these are possible in this network for some choices of the rate constants. It's not at all easy and obvious to answer when exactly it is globally asymptotically stable, when exactly we have a unique positive equilibrium that's globally asymptotically stable, but at least a sufficient condition was shown by kind of an ad hoc calculation by Peter Simon in 92. Once the rate constant satisfies this inequality, then there is a unique positive equilibrium and it's globally asymptotically stable. On the boundary of this set in parameter space, we have vertex balancing. So again, we still have global stability. In fact, if we apply the same machinery that I explained to you on the previous pages, the concept of disguised vertex balancing tells us that exactly when this ratio here is larger or equal to 1, that's exactly when this network is disguised vertex balanced. And in fact, this means that global asymptotic stability then can be concluded using the classical Horn-Jackson function. The proof by Peter Simon back in the 90s had nothing to do with the Horn-Jackson function. But this was a tedious calculation. He had to do all kind of estimates on several pages. I'll get back to this example later. Now, using this concept of disguised vertex balanced mass action systems, we get his conclusion pretty much like this. So how do we compute all these? And this is where our contribution comes in, other than kind of examining lots of examples in detail. We do have a suggestion about how to attack from the computational point of view. So let me explain that via the example of the partly reversible square. This is something that we have seen several pages back. And so I'm taking an auxiliary network here with rate constants lambda. And what I'm asking, this is just absolutely the same thing copied here from some pages back. I want to find all the kappas for which there exists lambda and x and y such that dynamical equality holds between the two ODEs, and the second one is vertex balanced. And as you see, this is a nonlinear quantifier elimination problem. It's linear in lambda, but it's nonlinear in x and y. The monomials come in. And my suggestion is first, instead of looking at this nonlinear quantifier elimination problem, let's solve just kind of a first step towards the solution and write these equations in terms of fluxes. What do I mean by fluxes? Those are the ones that I've written down here in the blue box. So for example, the flux on this edge here is, I'm gonna denote by beta. The fluxes on the first graph are gonna be denoted by beta. And it's the rate constant multiplied by the corresponding monomial. And I'm gonna denote the fluxes on the auxiliary graph by gamma. So with the betas and the gammas, I can express both the dynamical equality and the vertex balancing on the second graph. And the absolutely great thing about this is that it's all linear. Everything is absolutely linear, always. So this is a quantifier elimination problem. I want to find all betas for which there exists gamma. There's an existential quantifier, which I want to eliminate. But now the great thing is that it's a linear problem, and therefore you see it kind of immediately that this is nothing else, the solution is nothing else than just taking a polyhedral cone in R6 and then the positive part of it. I want all of my betas to be strictly positive. This polyhedral cone in this case, once we compute, this is what it looks like. Everything is linear here. We call it the disguised toric flux cone. And of course, we are not done yet, because from this point, we want to go further. And from the fluxes, we want to go back to the rate constants. That's our ultimate goal, usually. So we want to find all rate constants for which there exists x and y. This is going to be my positive equilibrium, for which all of these, I need to substitute everywhere here in the fluxes my rate constant times monomial things. So I still do need to solve a quantifier elimination problem. I could not, of course, and this is a nonlinear quantifier elimination problem, but I do claim that this is something much simpler than the original one was. I'm solving my original nonlinear quantifier elimination problem in two steps. First, I perform a linear step, and then I very much hope that in the second step, which hides the nonlinearity, is something that is simpler. And this is what we experience in practice most often, that the second step is going to be really, really much simpler than it looked originally. In this case, if we do solve this step, then turns out we need to find all rate constant values for which a positive equilibrium x star y star, or sorry, x y exists, where the first coordinate of the positive equilibrium is larger than a certain value, and at the same time, the second coordinate is between two bounds. If this is the case, that's exactly my disguised toric locus. And if I solve this nonlinear quantifier elimination problem, then this is what I get. I get disguised vertex balanced locus, or disguised toric locus. And this approach, again, the main idea is to split the nonlinear quantifier elimination problem into two steps. First, a linear step, then do a simpler nonlinear step. This approach proved to be very useful in multiple examples. For example, the reversible square. We know for sure that the disguised toric locus cannot be the whole parameter space, because an affine transformation gives us a parallelogram, and we know the parallelogram is not always globally stable, and we do have affine invariance of the disguised toric locus. And when I asked about a year ago or so one of our co-authors, Jashin, if he knows what the disguised toric locus is, he said it's just close to impossible to tell, because computationally it's so hard to find it. But turned out, if we follow our new approach and first of all, try to solve the problem first on the level of fluxes, then the first step one usually does is introduce something which we call calligraphic F usually denotes fluxes, and EQ here refers to equilibrium. So these are the equilibrium fluxes. Okay, so I do have by an equilibrium flux, obviously what I mean is I simply denote, instead of kappa 1, I write beta 1, just because that's the flux, that's the zero complex here. For this reaction here, I do need to write, instead of kappa 6, this I multiply by the monomial, so kappa 6 times xy, this is going to be my beta 6, and then I get an equation. Or if you like, this is the equilibrium fluxes are simply the kernel of the of the stoichiometric matrix. Okay, so uh, all the fluxes, of course, have to satisfy the equilibrium fluxes, the conditions for the equilibrium fluxes. But what I do want to see is the disguised toric flux cone, same thing that I showed you on the previous page, which is, turns out, all those equilibrium fluxes which satisfy something. I didn't write here on this page, that would take a little more space, take up a little more space to show you the whole calculation, but pretty much by hand, without using the computer, because it's a linear problem. You can do it by hand, and you find out that this polyhedral cone is the disguised toric flux cone. And once that is done, then you try to do the last step from the fluxes. You try to go to the rate constants. That's your ultimate goal. If you are able to perform this last nonlinear quantifier elimination problem, and in this case, turns out it is possible. It is actually very simple to do, and we did find in the end the disguised toric locus, which previously seemed impossible to find. We did find in the end. It seems I forgot to write here what how much of the parameter space is occupied by this large portion. I can't remember now the exact number. If we revisit for a minute the reversible Lotka-Volterra autocatalytor, I want to argue why the result that was obtained by Peter Szymon in the 90s actually follows from our considerations very, very, very easily. So if I take the set of equilibrium fluxes, that's just pretty simple to see that the flux on this reaction and that reaction must be equal for, no, sorry, not for the equilibrium fluxes. For equilibrium fluxes, there is a little more flexibility. But for being toric or vertex balanced, these must be equal. That's why Ft here denotes the set of fluxes which are toric or vertex balanced. So I need to take all the equilibrium fluxes where beta 2 equals beta 1. So that means the flux here equals the flux here. The flux on this edge equals the flux on this edge. The flux on this edge equals the flux on this edge. And that is not hard to see that this happens exactly when this relation holds between the rate constants. Now, if I take an auxiliary graph, I call it H1 this time, then I didn't write up here all the equations for dynamical equality, just some of it. So, for example, beta 1 is the flux here, and from that same source, this time I do have one reaction going forward, one reaction going backward, and the length of this is 2. So therefore, if I take some fluxes on this graph, which I denote by gamma, then gamma 1 minus 2 times gamma 9 must be the same as beta 1. This is dynamical equality at this source complex, or source vertex here. Similarly here, well, beta 2 is the flux here, gamma 2 is the flux here, and there is no other outgoing edge, so beta 2 must be gamma 2, and I have more equations to be satisfied for dynamical equality, but for my purpose now, it's enough to consider just these two. And additionally, for vertex balancing on the second graph, vertex balancing at this particular vertex here, the outflux is gamma 2, the influx is gamma 10 plus gamma 11 plus gamma 1. And from this, what I find is that beta 2 minus beta 1 is something that must be non-negative. This means uh, if I want to find uh, this guy's toric locus, then my only chance is that if beta 2 is larger than beta 1, the flux going back here must be larger, or at least larger or equal uh, uh, than what goes in that direction. And this construction here with this second auxiliary graph, H2, and my gammas are shown here in purple. So assume now that indeed beta 2 is larger than beta 1. The difference I denote by epsilon. And with that, if I take these flux values on my auxiliary graph, although they kind of look like betas and so on, but imagine these are gammas. So the gamma here equals, for example, to beta 3 plus epsilon. Then it is absolutely easy and straightforward to check that uh, this flux here uh, leads to a dynamically equal fluxes to the fluxes here, to the betas here. And the second one is going to be a vertex balance flux. For example, here you see the outflux is epsilon over 2. This also goes out, beta 3 plus epsilon over 2. That's a total of beta 3 plus epsilon. That's exactly what comes in. So indeed, outflux equals influx. And this shows me that the disguised toric flux cone is exactly uh, all those equilibrium fluxes where beta 2 minus beta 1 is at least 0. And from this, going to back to the rate constants, that's just a very easy exercise. And therefore, we found that the disguised toric locus is exactly this set here. And so there was no heavy calculation to be made during this process. I do not claim, and it would not be true for sure, that this is exactly the region of global stability in parameter space. The region of global stability is, I'm sure it's larger than this. This is a sufficient condition for global stability. Now, a four-dimensional example, which I took from a paper by George and Cassian from almost 2 decades ago. It has four species, X0, X1, X2, and X3. And back then, George and Cassian argued that it has a unique positive equilibrium, no multiple positive equilibrium for all rate constants, showing this they showed this by species reaction graph theory. On the other hand, the existence of positive equilibria we know because it's a reversible network. So we can conclude that there is a unique positive equilibrium for all rate constants. Do we know anything about global stability of that equilibrium? In a very, very tiny region of parameter space, if you compute the deficiency of this network, turns out it has a deficiency of 3. That means we need to satisfy 3 equations between the rate constants to be vertex balanced. And that's a really, really, really tiny part of parameter space where we do have vertex balancing. Now, can we find out the disguised vertex balanced locus or disguised toric locus of this network? Well, one, as before, starts with the equilibrium flux cone. That's something easy. The toric flux cone is within the equilibrium flux cone. You have to satisfy, again, 3 equations because the deficiency is 3. And if you do all the steps that I explained earlier, and solve the linear part of the problem, then you find that this guy's toric flux cone is something like this. This is just one, it unfortunately it didn't fit on one line, but this is just one inequality within the equilibrium flux cone. Not like three equations as before, just one inequality. And from this, what you can conclude is that the disgaistoric locus is full dimensional, 14 dimensional. You have 14 rate constants in total, and the disgaistoric locus is 14 dimensional, full dimensional, as opposed to the toric locus, which is codimension 3, as we discussed before. So we found a much, much larger set in parameter space where we do have global asymptotic stability. And by numerical simulation, we find that in fact we were able to cover 63% of the parameter space where we do have disguised vertex balancing and therefore global stability. What happens outside this 60%, I have no idea. Maybe it's always globally stable. We have not investigated in great details. We really don't know. And another thing that we don't know is what exactly the formula of the disguised toric locus in terms of the rate constants. So remember, this was just the first step to find this was the kind of the linear part of the problem, solving the linear part of the problem, finding the disguised toric flux cone. From this point on, one would need to solve still a nonlinear quantifier elimination problem to find the disguised toric locus, which we were not able to do so. Maybe we didn't try it hard enough, but this also shows the strength of our approach. Although the nonlinear part we were not able to solve, still we have a very, very important information about it. Namely, we know its dimension is 14, is full dimensional. And on the last few pages, just pretty quickly, let me show you a little bit of the theory after the many examples. So again, if we take the partly reversible square for illustrative purposes, then there is something which we called maximal weakly reversible realization graph. Well, there are 16, for this particular example, there are 16 weakly reversible realization graphs, not maximal, just weakly reversible realization graphs. What we mean by that is these are the graphs which can realize the original mass action differential equation with some rate constants. For example, if the rate constant here is larger than the rate constants here, then the net reaction vector is going to be something like this. And then, for example, with this reaction, I can realize it. So potentially, when I take my auxiliary graphs, which usually is I denoted on the previous pages by age, then these are the 16 candidates. In principle, I have to play the game with all 16 of them. But what we claim in our paper, you actually don't have to do it with all of them. There is always one among them which is the biggest one, a maximal one. If you consider these 16 graphs as a partially ordered set, which is induced by the subgraph relation, then there is always one sitting on the top of this partially ordered set, which is gonna be the unique maximal element of this partially ordered set, G max. And what we claim eventually is that it's enough to work with G max, in fact. So this page might be a little bit heavy, but this is this guy's toric flux cone, the same thing that appeared before. Here, for an original graph, I want to ask whether there exists an auxiliary graph H, which an auxiliary graph H and uh, toric flux, uh, toric fluxes on that auxiliary graph, such that the two are dynamically equal. Or I can ask the same question by fixing the graph H, and then the theorem, which was actually observed by Jashin and Polly and George in 2020 in a paper, that once you want to find vertex balance realizations or just weakly reversible realizations, the only thing you have to do is you need to go through subgraphs of the complete graph, source vertices of the complete graph. This is a big deal because this means you need to look at only finitely many graphs. You don't need to use what they call ghost vertices or phantom vertices, as uh, Gábor Szederkényi and Matthew called them more than 10 years ago. In fact, you don't need to take all the subgraphs of the complete graph, only the subgraphs of Gmax. And in fact, there is a little more than that. So we could prove that uh, the closure of the disguised toric fluxes is a pointed polyhedral cone, and you get the disguised toric fluxes exactly by taking the positive part of that pointed polyhedral cone. It is consequently, it is a convex set. It is relatively closed in the of the positive orthant of the edges, and additionally, you can find it just by concentrating on realizations using Gmax, the unique maximal weakly reversible realization graph. Once you have that, you just take the closure and the positive part, and also the relative interior of that is just given by this. So you don't need to take many auxiliary graphs. In fact, it's enough to take just one, and that's gonna tell you all the information that you are interested in. And this also lets us concluding some topological properties of the disguised toric locus. That's our ultimate interest, not the fluxes, but the toric locus in terms of the rate constants. So we do have a technical assumption, which is about the kinetic subspace equals the stoichiometric subspace for all rate constants. Uh, Let's not go into that. It's hard to check in general, but there's a large class of networks where we do know, for example, for weakly reversible networks, this is satisfied. And what we find is that once we take a state from a stoichiometric class and the flux, and in the very natural way, by dividing by the monomial computed at that state, we get some rate constants. This map is a homeomorphism between uh, the positive stoichiometric class cross the disguised toric flux cone and the disguised toric locus. And this tells us a lot of nice things. It tells us that the disguised toric locus is not something too crazy. It is a manifold with boundary, it's contractible and uh, connected set. More importantly, we find its dimension. It is simply the sum of the dimension of the stoichiometric subspace, or the rank of the network, if you like, plus the dimension of the disguised toric flux cone. So just by solving the linear part of the problem, that's already enough for you to tell some important information about the dimension of the nonlinear object that you are interested in. ultimately. The manifold interior of this set is just gonna be given by k dt g max. And it also tells you that the dimension of the disguised toric locus is the same as the dimension of the disguised toric locus when you take Gmax. That's your auxiliary graph, and you don't need to do the calculation with all the other graphs. And I'm nearing the end of my talk. So a little bit of the history. So I think it all started with identifiability of reaction network with the observation by George and Cassian back in 2008 that uh, the same mass action differential equation can be obtained from different graphs. Literally, the same equation might uh, arise using different graphs. Then Gábor Szederkényi found a small mistake in that paper, and maybe that made him kind of interested in exploring this further, and this kind of identifiability or non-identifiability kind of turn it to the positive, to our advantage. And they wrote a series of papers with Johnston and David Siegel and with others. Then renewed interest came about 6 years ago by George, Polly, Abhishek, and others around George. And this is where we are now. I presented our paper manuscript, which is currently under review. And we have multiple follow-up ideas which are in progress. I don't want to promise, but I very much hope by the summer, not end of summer, maybe beginning or mid-summer, we will come up with a second paper. And the take-home message is that the classical standard Horn-Jackson function is a global Lyapunov function more often than you would think. And of course, the picture here shows the level sets of the classical Horn-Jackson function in 3D. Thank you.